Welcome to UVU CS3060 Lecture 7.2, where we discuss the dining philosophers problem. This is one of my favorite synchronization problems because we talk about the starvation of philosophers. In this particular problem, we have philosophers that can sit in these 5 seats. And these philosophers can do one of 2 things. They can be eating or they can be thinking. Whenever a philosopher is eating, it will have 2 chopsticks. It's impossible to eat with just 1 chopstick. So in order for a philosopher to eat, it has to pick up both chopsticks. But a philosopher can only do this 1 chopstick at a time. So when a philosopher picks up both chopsticks, it's able to eat, and then it puts down the chopsticks when it's done so that it can think. So in our particular case, we have a data set, bowls of rice, 5 bowls of rice here, and we have semaphores, 5 semaphores, each initialized to 1, representing the chopsticks. Now, consider for a second that we have a philosopher that waits on chopstick on one side, then waits on the chopstick on the other side, then eats, then signals that they've finished with their chopsticks and lets them go. Now, what is wrong with this algorithm? Well, consider for a second that the philosophers can work at the same time. If I have one philosopher that's picking up a chopstick, but the philosopher next to them picking up their chopstick, when that second philosopher comes, they'll have to wait while the first, so the first philosopher picks up a chopstick, second philosopher picks up a chopstick. First philosopher waits for the second philosopher's chopstick. Now, if we have all 5 philosophers at the same time pick up 1 chopstick, and then all 5 philosophers try to pick up the other chopstick, all 5 of the chopsticks are already picked up. Thus, all 5 philosophers will end up waiting in a deadlock state, and thus the philosophers will not be able to eat, and they will die of starvation. That is what is wrong with this algorithm. We need to somehow figure out how to allow a philosopher to pick up chopsticks, but put them down if they are not going to use them. So there is a monitor solution to this. The monitor solution is to make sure that whenever you pick up, that a particular philosopher is checking to see if that particular if they're testing to see if they can pick up a chopstick. They're also a function for putting down a chopstick and going into the thinking state. The thing is, because we're in a monitor, these functions can only be accessed by one process at a time. This test function is going to test to see if the other philosophers are eating or if they're hungry. And it's going to only access those particular chopsticks if the other philosophers are meet these particular conditions. So using a monitor prevents a philosopher from picking up chopsticks when other philosophers are picking up chopsticks as well. So each philosopher will invoke its pick up and put down in this order. Now, we won't get a deadlock, but we could still get starvation because we could have a particular philosopher that's trying to pick up its chopsticks, is unable to, and has to wait for one of the other philosophers to put theirs down. But what if the philosopher on the right hand puts their chopsticks down, but the philosopher on the left hand picks theirs up? The philosopher in the middle still is unable to eat, and thus starvation. So we can do a resource allocator in this particular case so that we can acquire the particular resource that we want. If it's busy, we wait. Otherwise, we set the busy to true. And then when we release, we set busy to false, and we can go ahead and signal another process to come in and use the resource. This ends lecture 7.2, where we discuss the dining philosophers problem.